Now that we're in a new decade, let's start a new unit. Right?
Yep. No.
Okay. Yeah. First unit of the year. Last unit of the semester. Okay. So we have 8 school days between now and finals. In the next 13 calendar days, 8 of them are school days. Okay? One of those is conflict res day. One of those is the other Tuesday that we don't have class. So that narrows it down to 7 days. Okay? My plan for this unit, since you've all done this before, we've done exponentials and logarithmics, or you've done exponentials and logarithmics in Algebra 1 and in Algebra 2. We're going straight to solving. Okay? We're gonna remember some stuff today, and then tomorrow we're going solving. Monday we're gonna solve. Wednesday we're going to word problem. Thursday we're going to word problem and review. And Friday of next week we're going to test. Okay? So we're going to go right into a test next week Friday. Okay? Could be worse. My oldest is a 7th grader at Mirror. He's got a test tomorrow. Yeah. Yeah. They're giving a test. I'm like, why don't you just give him a test today? Same thing. You're getting the same amount of work. Thanks. Neither here nor there. And then that leaves us the following Monday, the 13th, to review first semester final. So you're only going to get 1 day for semester final review. Okay. What? When is our final? Either the 15th, the 16th, or the 17th. I know as much as you do. I'm sorry. They don't tell me. You think they tell me that stuff?
No, I already know most of my finals.
Yeah, they tell some of the teachers.
Yeah, I'm not one of them. Yeah. No, I had it at one point in time. I know it's right away in the morning. I don't know what day though. Something tells me it's day 1, but I'm not positive on that. I saw it at one point in time, but I'm like, I'm not worried about this until later. I know that I'm only giving the final in 1 period, though. Yeah. No, I'm having 1 option.
I only have 1 option.
Yeah. Okay. Buzzing going on up here. Must be some extra folding on the desk. Alright, so exponential and logarithmic. Anybody even notice it? Not quite sure why it stopped, but oh well, it stopped. Alright, so here we go. Now, this slide, you don't have to necessarily write down. Okay? Next slide, don't necessarily have to write down. Okay? I'll tell you when you start writing stuff down again. Okay? So if I'm talking about a linear function has a change that is constant. Okay? The change is never changing. If you're on the same interval, it doesn't matter where you are. So if you go from 1 to 2, like the difference is 10. Okay? If I go from 7 to 8, the difference is 10. If I go from 99 to 100, the difference is 10. Okay? The change is constant. The change doesn't change in a linear function. The slope of the line. Okay? Exponential functions, the change changes. Okay? If it's an exponential growth function, the change gets larger the farther out you go. If it's an exponential decay function, the change gets smaller the farther out you go. Okay? But the change is changing. And it's usually changing at a percentage. And we'll get into that a lot more next week when we get word problems. Okay? But for right now, the change changes. Okay? Again, don't have to necessarily write this down, but here is the difference graphically of a linear versus an exponential function. On the left, the linear function, the equation would be y equals 5x plus 100, or in this case it would be t, 5t plus 100. We'll just call it x just so that we stay in the xy plane. Okay. We've done a lot with that this year. You've done a lot with that over the course of your mathematics career up to this point in time. I don't think I need to go more into the fact that it's y equals mx plus b, b is the y-intercept, all that fun stuff. You know all of that stuff. Okay? On the other one, the exponential one, y here is going to equal 100 times 1.05 to the x power, or in this case, to the t power. Now, the big idea here is that when you are in an exponential function, and this is what I want you to write down, when you are in an exponential function, your independent variable is in the exponent. An exponential function has the independent variable in the exponent. That's the huge difference between these two. Numbers are numbers. The independent variable is in the exponent. Okay? That changes. That exponent having the variable in it changes the function. Okay? Makes the function grow faster than constant. Okay? So, we are going to talk about exponential equations and logarithmic equations in this unit. Again, I'm not going to go very deep into the difference between them. Just know the fact that an exponential function at its core looks like that. Or f of x equals a times b to the x power. Now, you might have some extra added-on stuff. We might have something like plus some number out here, and then it's divided by another number over there, and all that other stuff. But at its core, if you see the independent variable in the exponent, that is an exponential function. Logs and natural logs will look like that. Log base b of x or natural log of x. Now, natural log is just log base e. E is a special number in math. It's 2.718289828154, I think. Huh? base e. You can see it as log base e. You can have a stopover step, write it out as log base e, but in the end, it's natural log. Okay? Right? And we'll get into that in a little bit. Okay? The wonderful thing about these two types of functions is that they are inverses. Now, from your extensive mathematical knowledge, if I had to solve the equation x plus 7 equals 13, I would have to use inverses to solve it. Plus 7 is attached to the x, so I'd have to subtract 7. That's the inverse of plus 7. How we go about solving exponential functions is we use the inverse. We put it in logarithmic form. Same thing, if it's in logarithmic form, we solve it by putting it back into exponential form. Okay? I can tell an exponential function because the exponent is where the variable is. I can tell a log function because I see the word log, or I see ln. That's how you go about telling these things. Okay? Exponent or variable is in the exponent, it's exponential. See the word log, it's a logarithm. Okay? Alright? Now this slide is extremely important. I'd 4-star it in your notes. Okay? Because we are going to go about solving all of these problems by switching forms. So if we're in exponential form, we switch it into logarithmic form, and we can solve it. If it's in logarithmic form, we can switch it to exponential form, and we can solve it. So in exponential form, we have our base b, we have our exponent, and that equals some number. So we have b to the exponent equals some number, would be a common exponential function, or exponential equation, I should say. To change that into logarithmic form, I first start with the word log. Oops, my b forgot to move down. I want to really emphasize the fact that this b should be way down low by the g. Log base b of a number is equal to an exponent. You will hear me say numerous times throughout the course of this unit that logs are exponent finders. Okay? So that's why it equals the exponent. Very important stuff. Okay? Now, with that comes two rules. The first rule that we have in either of these forms is that b and the number have to be positive. Always. Just like Walmart. Walmart doesn't do always. Their slogan used to be always. Low prices. Always. Okay. So b and the number are positive. All the time. The exponent can be negative. But b can't be negative. And my number can't be negative. The second rule is that b can't be equal to 1. Because if it equals 1, the answer is just 1 to any power is 1. Okay. We're going to start out today by switching forms. We're going to end today by evaluating different equations. Okay? So, here we go. So, we're going to rewrite each equation into exponential form. Now, what I want to do here is give myself a little extra space, and then I'm going to say that the base to an exponent is equal to my number. Means the same as log of my base, or log base of my number equals my exponent. Color-coded. So, if I'm in, one of the things that is going to happen next week, Friday, on your test, is I'm going to say, switch forms. I know that I'm in logarithmic form, because I see log. Which means I got to go to the other form, which is exponential. Okay? So, I'm going to look for my base first. My base is 9. I'm going to look for my exponent next. In logarithmic form, my exponent comes over here. That's going to be to the 3/2 power. Then I'm going to look for my number in logarithmic form. That's right there. So this same equation written in exponential form is 9 to the 3/2 power equals 27. Good? Questions, comments, concerns, clarifications? Good enough, Leo, to do the next 3? Go for it. Try the next 3. Somebody give me the exponential form of number 2, please. What do you got? 7 cubed equals 343. Love it. Questions on that one? 100%? Speak now, forever hold your peace. Love it. Number 3. Somebody else give me a exponential form for number 3. Oh.
4 squared equals 16.
4 squared equals the greatest elementary school game ever. Not just 16.
Football was the greatest elementary school game.
4 squared.
I thought it was middle school.
What's wrong? 4. Anybody want to take a chance on 4? What do you got?
E squared equals 9.
Love it. Good job. Questions, comments, concerns, clarifications?
So why is it E?
Why is it E? Because it's natural log. And natural log is log base E. Right? So this would also be, we could also rewrite this as log of x equals 2.
Oh, that's right.
You know what I mean?
Yeah.
But we don't ever write it that way. But we think it. So sometimes when we think it, we got to put it down on paper too. It's like writing a paper.
Yeah.
Okay? Love it. Let's go the other way now. Now I give you exponential forms because I don't see log. Okay? And I'm asking you to put them 7 is my base. $49 is my number. 2 is my exponent. Log base 7 of 49 equals 2 is that answer. Somebody want to give me the answer for number 2? Log base 5 of y equals x? Somebody want to give me the answer for number 3?
Log base e 3 equals x.
Do we like log base e of 3 equals x? Because it's log base e? Okay? That would work. The log base e of 3 equals x works as a stopover point, but log base e is natural log. So the final answer here would be natural log of 3 equals x. Number 4. Ms. Stone, number 4. Questions, comments, concerns, clarifications? Love it. Okay. Now, logs are exponent finders. Okay. So we can evaluate logs like this. Now, you may be saying to yourself, how are we going to do this? Well, what we can do, or the way I go about doing it, is I usually say I'm going to set this equal to a box. And I want to fill up the box, dear Liza. Okay? So if I switch forms with this, that would be 2 to the box equals 8. What exponent would I have to put onto 2 to get me 8? 3. Yep. Because then that would be 2 to the box equals 2 cubed. So the answer here is 3. This method is called getting the same base. I have to remember how the book, or the NTC says it. Something about writing it as the power to the same base or something along those lines is that method that they call. I just call it doing the math. Okay? Find me or evaluate for me the other 3 logs. Anybody for 2? What exponent do I have to put on 11 to get me 121? 2.
11 times.
It was a good try, though. Can't, it's so far away. Number 3. agree? Anybody? What exponent do I have to put on 15 to get 1? 0. Yep. Number 4, what exponent do I have to put onto 1/2 to get 8? Anybody? Agree? But I thought we had a rule that said we couldn't be negative. What? The exponent can be negative, and this is an exponent. Because my base is positive and my number is positive. Exponent just happens to be negative. Yeah? One more. Roll. There is no exponent that I can put on 3 to get me 8. Right? I can guesstimate it. What would a good guesstimation be for the size of, or the valuation of this log base 3 of 8? 1.8-ish? Okay. 1.9, somewhere in that range. How do we know that it's between 1 and 2?
So you put 2, it's 9.
3 squared is 9,
Yeah.
and 3 to the first is 3. And 8 is between 3 and 9. Closer to 9, so it should be closer to 2. Okay? Alright? So in this case, when we have this, we've got to go about it a little different way. And that different way is we use what's called the change of base formula. Now, this is a calculator-based formula. Okay? This is for solving logarithmics using your calculator. Okay? Now, a couple of things about this. Log here, without a base, is the same as log base 10 of a. Okay? And since all numbers are base 10, that's why it's on your calculator, on the scientific calculator. Okay? So if there's no base written here, then that is assumed to be base 10. Okay? Natural log, ln, is also on your scientific calculator. If you have a phone, if you're stuck without a graphing or without a calculator, scientific or graphing, and you have your phone, if you tip it to the side, it becomes a scientific calculator. I think on all the calculator apps it does that. Okay? You wouldn't know. Because your phone's up here. Yeah. Okay? So with that being said, if I were to evaluate log base 3 of 8, I would say that that is either log base 10 of 8 divided by log base 10 of 3, or I would say that that's the natural log of 8 divided by the natural log of 3. And when I do that on a scientific type calculator, get 1.893. Which falls in that range that it should. Okay, we knew it had to be between 1 and 2, closer to 2 than it is to 1. Okay? Right in our wheelhouse. Just to play around with your particular calculator, let's find what log base 3 of 34 is and what log base 34 of 3 is. I get 3.210 as log base 3 of 34. And I get 0.312 for the other one. What's up? Questions, comments, concerns? Didn't get that on your calculator. Need some clarification. Parentheses make a difference on your calculator. Okay? Closing them, adding them in makes a big difference. Okay, just so you are aware. Okay? Today I have a worksheet for you. Okay? It's rather lengthy. It is due tomorrow. Yeah, but there's 22 problems crammed into the front side.
Sweet.
Okay. Had you paid attention in class today, which all of you I'm sure did, should take you about 5 minutes to do.